All right, guys, we'll look at this question quickly and let's solve 11 marks. Team is playing snooker and positions his cue so that the white ball is lined up with the black ball. Let me quickly check something here. There's a very important statement there, lined up, and it's very important because we are dealing with linear momentum, so it has to be on a straight line. That's where the line up comes in. A 0.6 kg white ball moving at a velocity of 0.5 collides with a stationary black ball of mass 0.8. On contact, the ball exerts a force. All right, the black exerts a force of 1.2 newtons, right? Okay, in this case now we are bringing in Newton's third law. If object A exerts a force on object B will simultaneously exert a force on object A equal in magnitude but opposite in direction. All right. So state Newton's second law of motion in terms of momentum. That's very simple. If you state the Newton's second law by saying when the net force acts on an object will accelerate, already you have a zero. Because they said in terms of what? Momentum. Anybody remember? Just change this into English. Can we change that into English? The net force is equal to the rate of change of momentum. And that's what you say. Because they said it must be in terms of momentum. 2 marks in the bag. If the change in momentum of the white ball is negative 0.24 kilogram meter per second, calculate the time that the white ball is in contact. All right, now let's check what we have. We have the change in momentum. What are we looking for? Let's make a list quickly. It becomes a lot easier. We have the change in momentum. What's our change in momentum? Negative 0.24. By the way, we have the force. What is the force? The net force. 1, and what are we looking for? Time. So what do we do? What do we use? All right, F net equals to what? Delta P over delta T. But let's be careful here because of the sign. Okay, if we go back to the question, it says the black ball exerts what? 1.2 on the white ball. Is that okay? So if we were to choose our direction to say forward as positive, it means this 1.2 becomes what? Negative 1.2 newtons. Why? It's a vector quantity. Very, very important there. Okay. Now, can we then say our F? Okay. If the change in momentum that calculate the time that the white ball is in contact. Now remember that they both exert the same amount of force on each other. So we are okay to then say this is what? Negative 1.2. What's our change in momentum? Negative 0.24 over what? Delta T. What's your answer for delta T? 0.21. Okay. Is it 208? 12 and 24, it's half. What did you do, Biggie? Okay, can we cross multiply? Negative 1.2 delta T equals to what? Then we divide so that we can see where if there is any discrepancy. It's 0.2 because 24, half of 12, 24 is what? 12. Out of 24 is 12, right? And I see that number here. 0.2 what? Seconds. Calculate the velocity of the white ball after the collision. Calculate the velocity of the white ball after collision. It depends on what we know now. What do we know? Okay. But we have the change in momentum, right? Okay, so if we have the change in momentum, do we all agree that change in momentum is what? M VF minus what? VI. Does that make sense? All right. Do we know the change in momentum? Negative 0,24. Do we know the mass? Which object are we dealing with, by the way? The white. What's the mass? 0,6. What's the final velocity? Do we know that? No. What's the initial velocity? And it's moving to the right, right? Minus 0,5. Make sense? All right, let's do the maths together. Can we divide by 0,6 both sides? What are we going to get? Negative 0,4 equals to VF minus 0,5. If we move that there, what are we going to get? VF will be what? 0,1 meters per second. I hope it makes sense. All right, number 4.4. On being struck, the ball moves forward towards the bumper cushion on the side of the snooker table and collides elastically. We did elastic collisions last week, where we had to do a question simultaneously, right? What is an elastic collision quickly? It's a collision where both momentum and kinetic energy are conserved. Please avoid saying just kinetic energy is conserved. No. Both momentum and kinetic energy are conserved. After collision, the kinetic energy of the black ball is 0,042. Let's get the question again. It is the black ball that collides with the cushion, right? And since it is elastic, we can quickly just conclude, since we're told that the kinetic energy before is equal to the kinetic energy after. So half mvi squared equals to what? Half m. Do we agree? Why am I using only one object? The table. The table is not moving. So it's 0 before and 0 after. All right, let's see. What are we looking for? On being struck, the ball moves forward towards the bumper cushion on the side of the snooker table and collide elastically. All right. After collision, the kinetic energy. So what is this? The kinetic energy after collision. Now we are looking for its velocity. This whole thing represents the kinetic energy after. 0, what? And half. What is the mass again? Of the, are you sure which one is 0,6? The white ball is 0,6, but we're dealing with a black ball, which is 0,8. And we are looking for what? Okay, what's your answer here? We cross multiply. No. Why?
No, because see, if you read the question, it says that it's stationary at first.
No. We'll go back to 4.4. Let's read again. On being struck, the black ball moves forward towards the bumper cushion on the side of the snooker table and collides what? Elastically. So that's the wall there. It's gone this way and gone back that way. Because it said, on being struck, the black ball moves forward. No. Right now, you are not being able to separate the motions. It was stationary before the white ball hit it. Read it. 4.4. On being struck, what happens? It now moves. The black ball moves forward towards what? The bumper cushion. Do we know that velocity with which it's moved forward? We don't. And what? Collides elastically with the bumper cushion. After collision, check. So we've already removed, somebody stole this white ball away, So we are only dealing with the black ball and the. So after collision, the kinetic energy is 0,042. Are we okay now? Can we get an answer here? Did you find the square root already? No. I need to find the square root. Zero comma meters per. All right, that wasn't bad. That was just a way of saying welcome, everybody. All right. Let's go for this vertical projectile motion. I'm going to. Here we have two. All right, please quickly read. Let's read the whole statement. Let's read Nomsa's story here. All right, everyone should have read. Okay, so Nomsa is standing. Let's read together again now. Nomsa is standing on the ground floor of a building. She throws a pencil case vertically towards Mekwe, who is standing on the balcony of the first floor of the building with an initial velocity v. All right, so that's the initial velocity of the pencil case. Mekwe fails to catch the pencil case as it moves upwards, then catches it on its way back. Ignore the effect of friction. The position time graph below, not drawn to scale, represents the motion of the pencil case when it was thrown up till it reaches Mekwe's hands. Choose upward as positive. Okay, so what happened now is the pencil case was thrown upwards. This is where actually Mekwe's hand is. But she failed to catch it on its way up. Generally, it's going to reach a maximum height and then fall back. Guys, it's not that the object is going this way. This is what's happening. The object is going this way and this way. That's all. So don't think that Mekwe is stretching to catch. She's not a goalkeeper. No. So it's a vertical motion. The object went up and came down.
So the other guy is standing like above her, like.
Yeah. So someone is standing here. Someone is standing here. Person one. Who's this? Nomsa, and Mekwe is standing here. Okay. So Nomsa throws the pencil case. It goes up, but past Mekwe's hand. So the pencil case becomes a free fall, gets the maximum height, comes back, and now Mekwe, being more professional, got the pencil case. All right. Yes, question? What is a projectile? No. A projectile is an object that experiences what? The force of gravity. So it's a projectile because the only force acting upon it is. So there are two types of projectiles. It could be dropped, but as long as the force the force acting on it is what? Gravity. It's called a projectile. It could be thrown. The force acting on it as well is force of gravity. So which also makes it a projectile. Okay? So a projectile is an object that experiences only the force of gravity. Same thing. No, free fall is a motion. Falling is not an object. When you say I'm falling, what are you doing? You are demonstrating it's a motion. Okay? All right. Use the graph to determine the time in which the pencil case. Okay, guys, this is one mark. They said use the graph. Determine the time in which the pencil case velocity is 0. When does it become 0? At maximum height. Do we have an answer? Yes. What's your answer? 1 comma? All right, please, let's put the unit. 1 comma 4 what? Seconds. Use the graph to determine the acceleration of the pencil case at 1 comma 4 seconds. What is the acceleration at 1 comma 4? It's a free fall. Anywhere. So examiner will always want to use the maximum height to deceive you there. Anywhere on this motion, acceleration is what? 9,8 meters per second square, and it is, that's your 2 marks there. 1 and 2. We need a direction because it's a scalar quantity. We need to specify the direction. Yeah. You would be penalized for negative. We want the direction, 9,8 meters per second squared. That's why when you finish your answer, you don't write negative, whatever. You interpret that answer. I'm not disputing the fact that it's negative 9,8, but what does the negative stand for? Downwards. So you cannot leave your answer as negative 9,8. It must be 9,8 meters per second square, downwards. All right, use the graph to determine the time it takes for the pencil case to reach McQuay's hand from the moment NUMSA 3 with. Let's see. Check this. It's just basic maths now. The time it takes. It's a parabola. We want the time here.
2.2 seconds.
All right, I've got a 2.2, I've got a 2.6, I've got a 2.8. Beautiful. Other answers from home? Those of us from home? Ashley, talk to me. BB, talk to me. The time it takes for the object to move up is the same time it will take the object to move down to where it left. So if you look at this, what is the time frame here? It means this one also should be what? 0,8. So our time here is what? And that is 2,2 what? Seconds. Please, I hope we are all okay with that. Idris, the time from here to here, the time it takes to go up is the same time it takes to come down, same point. So from here to here, 0.8, it has to be 0.8 as well on that side. And that's why we just added 0.8 and to give us 2.2. Very tricky. Somebody will just add and want to double that 1.4. All right. Idris, I hope it makes sense now. It is symmetrical. Yeah, from the moment she threw, it left, it missed Mekwe's hand after 0.6. So it went up after 0.8, in 0.8 seconds rather. It came back in another 0.8 seconds. So we just add all the time. 0.6 plus 0.8 plus 0.8. 2.2. Treat it like a mathematics parabola with a line of symmetry. All right, now let's calculate. Idris, tell me you're okay there. Use equations of motion for the graph. All right. And let's calculate. Okay, all right. The first one is to calculate what? The initial velocity of the pencil case. 3 marks. Everybody, let's walk through. We are looking for the initial velocity of the pencil case. It's 3 marks. We should be able to do that in 3 minutes. Let's make it 4 because of formulas. All right. Please give me your answers. We should be done. That shouldn't take so long. We are looking for the initial velocity. So you work where you have information. Okay. What do we have? All right. So let's check where we have, because there's no formula you would use. Since you don't have the displacement, you need two velocities there. I don't know the initial, but I know velocity at the maximum height, which is what? 0. And the time to reach the maximum height is 1,4. So I think we have all the information we need. Upward as positive. It means if we choose up as positive, g then becomes negative what? 9,8. Do we know initial velocity? No. Do we know final velocity? 0. Because we're working at maximum what? Height. It's negative 9,8. It's the same. Are you happy? Okay. All right. What do we know? Time. What's our time? So I think there's a formula here, right? What's the formula? VF equals to VI plus A delta T. What's our VF? 0. What's our VI? Unknown. Plus negative 9,8. And what's our time? 1,4. What is our answer for VI? Meters per second. And that's it. 3 marks there. 1, 2, 3. So it's all about making a list and having a boundary. All right. Calculate the height of the pencil case above the ground when Mekwe cut it. Can I go back to the graph? What are we looking for? The height of the pencil case above the ground where Mekwe cut it. Let's give ourselves another 3.5 minutes. We're looking for the height where the ball was cut. Here. The graph. The graph. Leslie, what are we looking at here? Okay, this child. All right, Leslie. You're welcome. All right, everybody now. What are we calculating? The height, right? Please, let's quickly work. Yes, you're correct, Mary. Anybody got an answer for me? All right, we're looking for the height, right? We're looking for the height. So, are you aware that the height here? Check something here. Are you aware that this is what we're looking for? This is the ground. That's where it passed Mekwe, and that's the simplest spot that she caught it. So we're just looking for this height. Do we know initial velocity? Yes. Do we know the time from here to here? What was it? 0,6. Huh? You are now, okay, guys, you could as well use 2,2. We are going to get the same answer. Because at 0,6, we are at a particular height, right? At 2,2, we are at the same height. If you use 0,8, no, you cannot. You know what you're doing if you use 0,8? You are looking for somewhere here. Because this is 0,6, then 0,2. So you're looking for the height somewhere here. Calculate the height. Okay, let's go read again so we get it done. It says, calculate the height of the pencil case above the ground when Mekwe cut it. Where she cut it was where it passed her hand. It passed her hand at 0,6. She cut it afterwards, 2,2. Any of the times would give you the same. You sure? Okay, let's do it together. Okay, just wait. What do we have? Initial velocity is what? 13,72. What is our G? Negative 9,8. What is our time? 0, what? 6. We are looking for delta y, right? Okay. What's your formula? YVF. We don't know final velocity. VI delta t plus 1 over 2. We don't have the final velocities. Nope. What's our VI? 13,72. What's our time? 0,6 plus 1 over 2, negative 9,8. What's our time again? 0,6. Okay, please, do you want to put that in a calculator for me? 6,47. Do me a favor, just go back to your calculation now and change that 0,6 to 2,2. Quickly. All right, so you see what happened, right? Whether you use 0,6 or 2,2, we're guessing the same answer. Because at those times, we are at the same what? Height. That is why it is displacement and not distance. Are we okay, everybody? Did that make sense? So somebody else could have worked with what? 2, 2 seconds. We are still going to get the same answer. I hope we are all okay. 6,47. Draw an acceleration time graph for the entire motion. Indicate. That's very simple. I love it. What? Okay. What do we have here? Time. And this is what? Acceleration. Are we aware that the acceleration is not changing? And what's the acceleration? Negative 9,8. So it's just one line and you're done. I don't know why you guys are complaining. This is negative 9,8 and we are done. That's 0. The acceleration is constant. Okay, guys, are we okay with what I did here so far? Our solution is negative 9,8. Can we give an answer to the last question? Can we give an answer to the last one? Then I'll draw a VT graph. Now, what does the area under the acceleration time graph represent? What do we do? Area. I know. Oh, by the way, guys, this is incomplete. We are supposed to show the time here for the entire motion. I think it was 2,2, right? Yes. Now, what shape is this? Rectangle. Good. So when they say area, we are simply looking for length times what? Breadth. What is this? Acceleration multiplied by what? Time. The question is, does that formula exist? No. Now, check this. VF. What is acceleration? Acceleration is what? Delta V over delta T. Let's cross multiply. Change in velocity equals to what? A multiplied by what? Delta T. It's not velocity. It is change in velocity. It is VF minus VI. That's the answer. Yes. No. Area. I taught you how to deal with graphs. I taught you 3 ways of doing graphs. Multiply, divide, rearrange. Guys, so are we okay? Area, just multiply the y and the x and see where it leads you. Now let's draw a velocity time graph for the motion of this ball. In drawing a VT graph, let's make it very simple. Let me show you what to do when they ask you to draw a velocity time graph. It's so simple. Completely simple. Our graph looked like this. Let's make life very difficult. Life is very simple. This is what we had, right? What's the initial velocity there? 13,72. What's the velocity here? 0. Now, we didn't calculate this particular velocity, right? But definitely it is going to be lesser than 13,72. What was the time here? 1,4. And what's the time here? And okay, we do not need that when we draw this velocity time graph. And that, guys, now it's very simple. Can we write all the velocities we know? What is this? 0. What is that? 13,72. All right. What time do we know? 1,4. And then what? 2,2. When the object was thrown up, started with that. After 1,4, it reached the top. And then what happened? It stopped at what? 2,2. I'm trying to just gauge that. And we are done, guys. We didn't calculate it, so it's not necessary. We didn't calculate that. Okay? And that's your graph, guys. Now, if there's a bounce, I'll show you what to do with the bounce. But that's how simple this thing can be. It's very, very simple. Now, let's create a bounce. Okay? Let's create a bounce. So this is where this is how the object is. I don't know if it makes sense. You look at important points on your graph. This is point A, point B, and point C. And you can also trace that. Point A, point B, and what? Point C. Before we go and look for the bounce, let's do something. We looked for the height. We check this. Height of the pencil case above the ground when Mekwe caught it, right? Okay, where did Mekwe catch this thing? Somewhere here, right? Good. Between A and what? C. All right, check this. Between A and C. Oh no. Okay, because I don't have that velocity there. I wanted to. Do you think we can calculate this velocity? No. We can. By using gradient. What's the gradient here? Negative what? 9,8. So gradient is equal to, this is our V, right? And this is our time. Y2 minus Y1, which you can say V2 minus V1 over what? T2 minus T1. We know this is acceleration due to gravity. So it's negative what? 9,8. Are you working with me? What's our V2? 13,72 minus V1, which we don't know. What's our T2? Remember, this is 0.2. I'm using that as 0.2, and I'm using this as 0.1. So my V2 minus V1, where's X2? 0 minus 2,2. Can we do the maths together? Negative 9, let's cross multiply everybody. 13,72 minus VI equals to, what is negative 9,8 times 21,56? All right, can we get VI now? We move that over to that side. No, not VI, V1. All right, V1. What's your final answer? Negative? Why are you getting 35, baby? Aren't we moving 13,72 over to that side? What are you taking over? Just take the 13 over. 7,84. But it was minus VI, right? Minus V1. So what is our V1? Negative 7,84 meters per. Do you know why is that? Do you know why we're getting negative? Okay. Where is point C? The object is now coming where? Down. I want us to quickly use equations of motion to get that done. All right, let's use equations of motion. Let's use equations of motion quickly. Do we know the final velocity there? No. Right? But do we know our initial? Let's make a list of what we have. VI equals to what? 13,72. Our time frame is what? 2,2 seconds. Right? Okay, what else? We're looking for VF. And we know our G as negative 9,8. Everybody, let's work together. VF equals to what? VI plus A delta T. What's our VI? 13,72 plus negative 9,8. And what's our time? 2,2. Please confirm your answer. You must be getting negative 7,84. All right, so this is me just trying to use the graph and using equations of motion to. Yes, we can use that as well. We are going to get the same thing. So please remember what the gradient is here. It is negative 9,8. Are we okay so far? All right. It depends on your direction. And if we take you back to mathematics, analytical geometry, look at the shape of the graph there. It is a decreasing function, so it is negative. Let's quickly do a question where the object, I'm just going to create a scenario where the object is bouncing so we can sketch the graph. Is that fine with everybody? All right. So let's have a scenario quickly where the object is bouncing. So do you want us to throw it from the top or from the ground? Okay. We need to agree. Do you want me to drop the object? You want me to throw the object? Give me a scenario. You want me to drop? Throw. Okay, throw up. Okay, so I should throw it up from a particular point. So it goes there, and then it bounces, right? Okay. Question is, do we want it to bounce at the same time, or do we want it to bounce after a set after? Okay, let's do both. Okay, so it bounces, all right. And the second one that we will do is to say it stays on the ground. Is that fine with us? All right. Let's give it velocities. What's your initial velocity? Give me an example. Give me a value. Oh, Fahima, 7,5. All right. 5.9. You have to put all the decimals. Wow. Very lovely. Meters per second. What would be the final velocity? Definitely it's going to be, if I choose upward as positive, downward would therefore be negative. And it will be higher than 7,59. Negative 10,21. You're so weird with your values. All right. Now, it's going to bounce up again. At what velocity? It's not going to be the same. Because now, the way I drew it, it is inelastic. So, energy has been lost. Let's say,
If it bounced back up with 2,5.
how can it be 2,5? And then gets to what? 0. Okay, ladies and gentlemen, let's look at the important points. A, B, C, D, and what? E. Do you understand what my CD is? The values are different there. Let's create a time. We're just checking on this graph, right? We're creating values. Let's create a time here. 2 seconds, okay? And then here, it cannot be 4. Okay, 6 seconds. And then here, Fahima. Okay, 6,07. Yeah. No, it bounces at the same time. There, this is where we're going to create the change.
So make the other one 9,21.
9,21. All right. You guys should not become teachers. Going to frustrate the life of kids. Okay, check this. Look at this. I want to draw a graph, right? Fahima? What are the velocities that you can see here? 7,59, right? I don't know why we have to choose weird values. 7,59. What's the next velocity? 0. What's the next velocity? 10,21. And what's the next one? 8,25. All right. Now let's go right. No, we'll deal with the time as we cut so that it's because it's not going to be perfect. Okay, our first velocity is there, right? Then it became 0 after a while. That while is what? 2 seconds. Make sense? Okay. Then it became negative after 6, right? Okay, what I will ask you to do is, please, it's a straight line, so do that. So that you can get it perfectly. I'm going to draw that, and I'm going to draw that. Now, what is this time? 6,07. We okay? Now, do you notice it is at that same time that the velocity becomes what? 8,25. So at that same time, 8,25. Okay? And then it becomes what? 0 again after what? 9,21 seconds. And that's all you're doing. So I'm going to just show that that line is straight and start the second one from here. And we're done. And these two lines, don't do this, but these two lines are supposed to be what? Parallel. Why? They have the same gradient. Because they both represent acceleration due to gravity. And we're done. So make a list of your velocities and the right timings, and then you're good. Let's quickly draw this one. 7 seconds. 7 meters per second, right? Okay, this one dropped. No, this one dropped. Okay? So initial velocity is what? 0. What's happening while it's dropping? The velocity is increasing. Let's say it hits ground at 7,5. All right? Bounces back up at maybe 3,2. Fahima, your bug is now beating me. What? These are just what we didn't calculate, right? Okay. Now, what time? Let's create a time here. We said 2 seconds. It stays on the ground for 1 second, and then that means it bounces after how many seconds? 3 seconds. Reaches the maximum height, and we have, let's say, 7 seconds there. We're just creating values. Let's see what the shape of the graph would look like. It's not abnormal, BB. It's you'll see the difference. All right. Guys, I hope you're seeing what I'm doing, the little trick I'm using, right? I'm always writing my velocities. What's the first velocity there? 0. Then the object, 7,5. 3,2. All right, 3,2 there. Is that fine with us? All right, what would it look like? We're starting from what? 0. Then we go to 7,25 after 2 seconds. It depends on, okay, if we right now, because we said positive, we have chosen down as positive. 7,5. Yes. Oh, yeah. The 3,2, because it's now going up. So if we choose down as positive, this is positive, but it goes up now at what? Negative. Thank you. Negative 3,2. Okay, so we started at 0, right? Object got to 7,5 after how many seconds? 2 seconds. Okay, we're done there. Object stays on the ground for 1 second. So it only gets to, that's 3 seconds, right? At 3 seconds, it is now negative what? 3,2, which is right here. And then it goes back to maximum height after how many seconds? 7 seconds, which is now there. All we are doing now is joining the graphs. Where are we starting from? We go there, right? Are we okay? And we go there. But you will then use dotted lines to show this time frame. And we're done. Check here. The time frame is a vertical line, which means it bounces off immediately. But once you see that line slanting, that means it stays on the ground for that time frame. Yeah. It's important that you show it. Are we okay, those of us at home? Any question? All right. Are we okay so far? Let's see. Let's pick some questions. All right. Biggie, we'll go to your question. Biggie has a question, and I think it's on photoelectric effect. But before we go there, I want to do a lot of velocity questions today. Let us pick. I did one yesterday, and I don't remember. 1 second. I think it's Western Cape. All right, let's just quickly check. And if there's anyone who has any special one on all of this, I just want to do one more of this. Then we look at. We did Newton's laws already, right? Yeah. If you can tell me where the question is, Leslie, we can. I don't want you to. You'll be giving me something probably you misinterpret wrongly. All right. Let's try one that I saw. I hope I will be able to get it. All right. Okay. Someone suggested this. All right, guys, quickly, please, let's go through together. Everybody. Let's start reading. Tesmia, let me see what you sent me. Okay, guys, quickly, let's have this question. Tesmia, I got it. September 2016.
It's not matter, mas esse é nível.
All right, guys, let me just see if I have that question. There's another question here. So we have two questions. Then we can try. Biggie, then we'll go to yours. Okay? I'm in a hurry to get you your answer. Leslie, please send me the question and I'll be able to do it. When?
So you said I'll do it after exam.
Okay, I'm looking for Leslie's question. No, this is a different one. Sorry, guys at home. There's the,
They're like 24/7 and it says 25/8.
Exact. Or what?
I mean, it says like.
I don't know. There's one at the bottom. It says 2 hours.
um,
Oh, only.
this is Western Cape. They have different metros.
New Metro.
Okay, all right. Can we let's? I'm going to ask you to send it to my email so that I can download it. All right, just a second. All right, guys. Let's quickly sort this question out. Please, 10 minutes so we can work it out. I need answers to this. Everybody, we're working now. We're working. Let's make it. Let's make it 12 minutes. Please, I want to see how many marks you'll be able to get here. Please, I need everyone working. Okay, everybody, now let's quickly answer. We have 44 seconds, so I'm taking that away. A rescue helicopter lifts a man. Please, guys, I want us to understand this concept. They are very easy to deal with once we understand. A man 75 kg, initially at rest. Let's start interpreting. Initially at rest, what does that tell us? Initial velocity equals to what? 0. And how are we moving? We're moving vertically where? Upward. By means of a light, inextensible, massless cable. Inextensible cable means there's tension there. And the tension is also the applied force. All right? While the man is lifted a height of, so we're moving up, right? A height of what? 12 meters. The average tension in the cable is 3,000 what? 600. A constant downward air resistance. Makes sense. Why is it downward? Because the man is being lifted upward. So friction is always against the direction of motion. So can we say our air friction therefore is what? 1540 newtons. Is exerted on the man when he is lifted. Guys, look at what I have done. Some of you started from 5.1. And because you could do that without reading the thing, you continue. But 5.2 now became a problem. Draw a free body what? Diagram. Hi. How many forces are we looking at? Leslie.
So basically, right, you follow air resistance as friction, right? So like anything opposing would they instantly count as a non-conservative force.
Friction is a non-conservative force. And that's what we mean by air resistance. Resist means friction. Yep. So which forces are we looking at? Talk to me, everybody.
So it's tension up, there's friction downward, and it's
Is your diagram looking like this? FG, FK, and tension. We're done. 3 marks. Make sure it all comes from a dot. Guys at home, please ask questions. I hope you are marking as well. Name a non-conservative force acting. There are 3 of them that we know, right? We said they are FET, right? Don't write FET. Please, examiners don't know what FET is. Okay, but we know we are talking about what? Friction. Applied. So which one do we have here? We have both. So you could mention any of them. Yeah. Calculate the work done on the man by what? Gravitational force. The work done by force of gravity. Can we get a fresh page? Now, if we are looking for work done by Fg, what's the formula for work? It is F delta X. All right. But this time around, it's Fg. That's my force. And it's not delta X. It is delta Y because it's vertical. And then we have what? Cos theta. It does matter. I will. Sorry? Huh? Which one? Why is cos? It's a formula. Check your formula page. W is F delta X. This is the general formula for work. Now we tailor make it to which force we are dealing with. So if it is gravity, then force becomes gravity. This is not delta X. Delta X means horizontal. This is vertical. And cos what? Theta. Where theta is the angle between the force and the what? Displacement. Do we know? And we know Fg is mg, right, everybody? Do we know m? 75. G is, and what's the height? 12. Now let's go check this. How is the object moving? The object is moving where? Upwards. Delta Y. This guy and the T are in the same what? Direction. Basically, this is what you just need to remember. Friction will always be 180. Any force that opposes friction, just put a 0. That's all. For friction, we would always use what? 180 degrees. It means this one will also be what? 180. This one becomes what? 0. Makes sense? So use friction as a guide all the time. No. My angle is 0. The displacement is going up. Oh, sorry. We are using gravity, right? Sorry. Gravity is going to be 180. Okay. So what's our answer? Negative 8820 joules. All right. So the work done by gravity is actually, do you know what the negative stands for? The negative simply means, no, it's not downwards. Let's quickly explore this. Energy is, sorry? Lost. I had some. Okay. Energy is a scalar quantity. All right? Energy is a what? Scalar. The negative simply tell you that energy is removed from the system. Removed from the system. Please, when we do this, don't say downwards or upwards. The negative simply tells you energy is withdrawn, removed, taken out of the system. That's why we say it is doing a negative work. And that's why the object will always slow down. Let's quickly explore. Energy removed from the system reduces the speed of the object. Reduces the speed of the object. This is what happens. This is why when there's friction, the object slows down because we are removing energy from the system. That's why you always get negative value. Are we okay, everybody? No. All right. Are we okay, everybody? Good. So we are saying gravity is removing 8,820 joules of what? Energy. Make sense, everybody? Okay. Are we good? Is the angle making sense to us, everybody? All right. So now let's use only energy principles to calculate what? The speed of the man at 12 meters above the ground. Once you see energy principles, let's walk through. I just prefer work done by non-what? Conservative. It's not the only one. We can use all others. Okay, Bunga, I'm going to help you because I see now where you made a mistake. What are these? They are non-conservative forces, right? I want you to get it today. How many non-conservative forces do we know? Friction, applied, and tension. But in this question, how many do we have? We have 2 of them. So we are going to be saying work done by what? Friction, plus work done by what? Tension. You see, I'm listing them. And this is equal to what? 1 over 2 m Vf squared minus Vi squared plus what? Mg H final minus H initial. Are we okay? All right. Can we now expand our work formulas? We are still using that same work formula. What is the work formula? W equals to what? F delta X, or in this case, delta Y, right? But which force am I dealing with here? Friction. Bring all that thing in. What am I going to have? Friction, delta Y, cos theta. You see? Plus, can we do with tension? What will it be? Tension, delta Y, cos what? Because it must be work. Equals to, I'd just like to substitute all at once when I do my substitution. Now I am going to need you. Let's substitute together. Remember, the object was first on the ground. Is that okay? And then moved to a height of what? 12 meters. We agree, everybody? So where is the initial and where's the final? That is the initial height. And that is the, what's your initial height going to be? 0, because the object is on the ground. Guys, if you just learn to interpret like this, it's too nice. Too nice. Do we know our frictional force? Yeah. What is it? 1. Please don't come here and say negative. No. This is work. All the forces are positive now. Is that okay? What is our displacement? 12. Fumani, focus. What is the angle here? Cos 180 plus, what's our tension? 3,000 what? 600. What's our delta Y? 12. Cos what? 0 now. Do you see where your free body diagram is playing a role? Okay. Equals to half. What's the mass? What's the math? 75. Do we know the final velocity? No. Vf squared. The object started from rest. 0 squared. Plus, what's the mass again? 75. What is our g? 9,8. What's our final height? 12. Guys, do you understand the easy way of doing this? Just get all your formulas right. Mary, are you trying to say something? Can we all calculate? Please put all the one on the left hand side. Let's all confirm in our calculator. Just type the whole thing in. Two four 20. All right, equals to, this is 37,5 VF squared. Now give me the whole thing here. 8,000? Oh yeah, we got that right. And 20. Can we then bring this here? Let's subtract. Okay, please let's just confirm the way BB is now sounding. Okay. So what do we have? 15,900.
It must be negative 8820 on top.
37,5 VF what? Squared. Can we divide both sides and find the square root for me? Why are we lost now, Tesmia? Remember, final height and initial height. That's what tells us whether it's negative or positive. 20, comma. Did you find the square root already? Meters per what? Second. It's so easy if you just understand that first part. All you are doing is expanding the formula and breaking it up. Are we okay? Are we okay, everybody? Fumani, question? Guys at home, please let me know, does this make sense to you? All right. Okay, I have a question that. Okay, no, we're not doing. The one you sent me now is a vertical projectile motion, right? Okay, let's do focused today. Then with our next session will now be. All right. Okay, here we go. You sent me a memo. Tesmia. I should answer the memo. This is Metro North. Metro North. This is it. All right, this is Metro North 2016.
What's the memo I sent?
No, but this is not what you sent me. No. Okay, which question am I looking at here? This. Yeah, that's what I'm saying. You should please resend it to me. Sorry, guys at home. There's just a question here that. All right, just one question and then we can. I have Biggie's question. Are you sending? Guys, if you also have question that you want us to do, please send it. It's gonna help.
I'm not sure we can open it. I was joking. The same way.
Okay. All right, let's see. There's a vertical projectile motion question that Mosam want us to quickly look at. Let's see if it's this one. No, this is the same one I had. Okay, let's check the second one. All right. Let's see this. All right, I think it's this one, right? Okay, beautiful. Guys, let's have some fun. It's time for fun again. Okay, let's look at this question together. I do have this paper. All right, just trying to get myself a fresh page. Just 1 second, guys. Okay, let's go screenshot. Where were we? Here, right? Okay. Guys, I'm going to do this with us quickly as time is just not on our side. Okay, there we go. Beautiful. Is it visible enough? All right, let's see. We're going to read together and try to interpret together. I'll be waiting on you for step-by-step interpretation. Okay. A ball of mass 100 grams. I'm going to stop there quickly. We don't work with grams in physics. What do? We convert to kg. So can we convert that to kg? Mary, please, if you can send me the question, I'll appreciate that. All right. What's our mass? 0,1, right? Kg. Okay, so a ball of mass 0,1 kg is thrown vertically upwards from the ground with a velocity of 3,92 meters per second. I want us to take it and understand every statement. So what are you seeing now? A ball is thrown up. Okay. The graph below illustrates how its velocity varies with time during the first few seconds of its motion. Please look at the graph. Do you notice, this is the first thing that piques everyone's eye, is that vertical, if I draw two vertical lines there, do you see that they don't meet? Do you see that, right? If I draw straight lines where the velocities are ending there, it simply tells me that in that place, object was on the ground. Or object is on the ground. That's what we quickly figure out very fast. When the ball hits the ground for the first time, it is there we go. It is in contact for 0,1. And that's the 0,1 there. All right? Define the term projectile. An object that experiences only the force of gravity. We're done. Calculate the maximum height reached. Okay, you want to go for this? Try it. Maximum height reached. Wait, let's do something. Before we start calculating, everybody hold on. Can we quickly transcribe this into position time graph? What do you notice? The object was thrown where? Vertically upwards. Okay. Thrown vertically what? Upwards. So this is A. That is B there. Why is that my B? Maximum what? Height. I want you to check something. What happens? There's a change in direction, right? But look at this. What is this? 3,92. What is this? Negative. It means the object reaches the maximum height and bounces. We are at the same level. It's 3,92 and negative 3,9. So this is my 3,92. That is my 0. And this is negative 3, those are the things you check. If it was not 3,92, it means probably greater than 3,92. The object was thrown from a cliff or on top of a building and goes down, like the first one we did. All right, if this one was negative 7,1, it means that's what we have. So right now, we are sure of the position. So that is my what? C. Make sense? But do you notice C and D are not at the same spot? It means the object stays on the ground for 0,1 seconds and then bounces back up. This is now D. At what velocity? Check the velocity at D. 2,5. And then E. 0. Guys, do you see what I've done? If I was supposed to draw a VT graph, I would have to move from that side back to a VT graph. So it makes sense to see your diagram like this quickly. Do you want to calculate the maximum height for me, please? Number 3.2.1, everybody. Okay, everybody. I have an answer here already. All right, maximum height, the ball reaches above the ground. What do you know about maximum height? Final velocity is what? 0. Do we know our initial velocity? Yes. So we're done. What formula do we use? Okay, let's check. Guys, can you pick? Let me ask you something here. Can you identify? Everybody look up here. This is very key. Can you identify the direction that they have taken?
Yes, they're taking up is positive because gradient is negative.
Good. Gradient is negative. So our A is negative 9,8. It means downward is negative. That's very important. So the examiner has chosen upward as I received a question now that I would love to do. It's a hot air balloon question. Okay. All right. So, can we make a list quickly? Let's run. Time. What's our initial velocity? 3,92. What's our final velocity? 0. What else do we know? Negative 9, what are we looking for? Delta y. Do you see a formula? What is it? Vf squared equals to what? Vi squared plus 2a delta y. 0 squared equals to 3,92 squared plus 2 negative 9,8 and delta y. What's your answer? Do we agree? Please confirm. All right. Time taken by the ball to reach the ground. Okay, quickly. 3.22. Come, let's run. Let's run. Time taken. Time taken. Time taken. Everybody, please, let's work it out. Let's work it out. Let's work. All right, please, everybody, guys online, get the time and send me your answer, please. All right, time taken by the ball to reach the ground. What do we know? 0, comma? No, it depends. Okay, let's clarify that. You don't just always multiply by 2. It depends on what you are using. No, okay, baby, just wait. What's the velocity here? 3,92. What's the velocity here? If I'm using these two velocities, I don't need to multiply by 2. Okay, hold on. That's why I said there are two ways. What's our initial velocity here? 3,92. What's our final? If you are using 0, then you are stopping here. That's when you multiply by 2. But if I come here straight, then I'm not going to multiply by 2. So let's take note of the difference. If I stop at 0, it is halfway because of maximum height. Whatever time I get there, I multiply by 2. But if I know this velocity and that velocity, there's no need. So what do I know? Vf equals to Vi plus A delta T. Work with me. I need you. Equals to what? 3,92 plus negative 9,8 delta T. So let's know when to multiply by 2. What do we have here? Negative 7,84 equals to negative 9,8 delta T. What's our time? 0, comma? Biggie, if you use final velocity as 0, it means you only calculated up to half. So let's get the difference in those velocities. Here, maximum velocity is velocity at maximum height is what? 0. So if I say Vf equals to Vi plus A delta T, what would I have? 0 equals to what? 3,92 plus negative 9,8 delta T. Somebody give me an answer quickly. 0,4. But what have you done? You have calculated just halfway. To reach the ground, we need another what? 0,4. So you come to which is what? 0. So let's know when to multiply by 2 and when not to multiply by 2. Let's run quickly. Calculate the magnitude of the force that the ball exerts on the ground while it is in contact with the ground. Now, once you see a question that is talking about force, you are going to bring in F net equals to what? Delta T over, so delta P over what? Delta T. But I want you to read something. It says, while it is in contact with the ground. This is why if you learn to draw, oh no, where is my diagram? If you learn to draw, it makes a lot of sense. Where is it in contact? Right here, CD. So if I look at CD, this becomes my initial velocity, and this becomes my what? Final velocity. So examiner is talking about force there. So what do we do? F net, right? Let's quickly work. There's a question. I want to get us to do that question together. F net equals to what? Delta P over what? Delta T. And what are we looking for? Delta P is M VF minus VI over what? Delta T. What is the mass? 0,1, I remember. Final velocity, 2,5 minus. Let's go back. What's the initial velocity? Negative 3,92. Don't forget your signs. Between C and D. All right. So what do we have? Negative what? 3,92 divided by what? 0,1. What's our answer? Yeah, it's given. And we extracted that out at point D, 2,5. Guys, are you aware that I'm done with 3.4? 3.4 has been done. Labeled even. Draw a position time graph. Indicate all the times A, B, C, D, E. I'm going to go get that question now of hot air balloon. And Biggie, maybe we can do your question in the next session because now we cover photoelectric effect. Okay, we'll try if there's time. What's our diagram looking like? We started from the ground, right? Is that right? We stayed on the ground. And this is A, B, C, D, and E. Do we have all the times? Time it reaches the maximum height, 0,4. Time it goes back to the ground, 0,8. It stays how many seconds on the ground? So what do we have here? 0,9. Do we know the time frame at the end? All right, we don't know the entire time of travel. Okay? No. Time. Velocity is 0, not time. Yeah, I think we're fine because the times that we calculated, we have actually shown all of them. We did not calculate the. So what is this? Position what? Time graph. And what's on the y-axis? Position in meters. Ground is the reference point. And what do we have on the x? Time in seconds. All right, guys, can I go to that hot air balloon question? I hope it's making sense as we're interpreting together. There we go. Why do you hate the hot air balloon? I'm going to make sure you get married in one. All right, there we go. Let's see. All right, ladies and gentlemen, let's quickly work this out and then we'll shut down today. Oh, we will. So we are answering the questions like we're finishing now. Okay, then Biggie, I'll definitely answer your question. Biggie wants me to deal with November. No, it's multiple. Okay. Let's quickly answer this question. A hot air balloon is rising vertically. What? Can you see? Fumani is going to create an excuse. Let's create something for him. I don't want your excuses. Because already shaking his head that he can't see. All right. So, Fumani, any excuse now? No. Good. Okay. A hot air balloon is rising vertically. Please, guys, I'd like you to pay attention to those words. The first thing is at constant what? Velocity. What do we know? Acceleration equals to what? 0. When the hot air balloon reaches point A, a few meters above the ground, a man in the hot air balloon drops a ball which hits the ground and bounces. Okay, I want us to, before we even look at the graph, how is the hot air balloon moving? All right, let's quickly look at very important thing here, and I don't know if they will ask in this question. How is the hot air balloon moving? Upwards. Okay. So check this. What did we do from the hot air balloon? We what? Dropped. Two important things. The initial velocity is not 0. The initial velocity is the same velocity as the hot air balloon because whatever we dropped was moving. Number 2, when we drop it, it doesn't go down. According to Newton's first law, an object will continue, or an object will remain at rest or continue uniform motion unless acted on by an external what? So when we drop this object is first going to continue up and then come down. Please, let's take note. This is what happens. All right, lovely. This is the same thing that happens in a car when you sit down and the car is moving. When they stop the car, what happens? You continue in that motion first before you retract. Tesmia, when the car stops, yeah, so it's exact same thing. So only that this one is vertical, but when we are in a car, it is what? Horizontal. It's the same thing. So when you drop, Kwanele, what you say? Yeah, Kanjalo. It's Newton's first law. An object will remain at rest or what? Continue in uniform what? Motion. Remember, the hot air balloon is inside here. How is it moving? It's moving up. So when we drop it, it's still having. Remember, okay, guys, let's do this. Let's say the initial velocity, or let's say this thing was moving at 10 meters per second. It means the stone or the ball is also moving at what? 10. That means this object is also still moving at what? 10. How is this thing moving? 10 meters per second where? Upwards. It means the uniform velocity here is 10 meters per second where? Upwards. So it goes up first, reaches maximum height, and then turns. Let's see the graph. The velocity time graph below represents the motion of the ball. All right? Gravity. Gravity is pulling. Now, check. Already, do you see the initial is 5.88? it continues until it gets to what? 0. When will it get to 0? It was moving up. They will even ask you, so I've seen that asking some question, why is the object moving up? It's moving up because of what? Newton's what? First law. Newton's first law. Yes. Newton's what? First law. Remember inertia. The resistance of an object to do what? The tendency of an object to resist what? Change. Is that okay? So when you drop the object, that's why we needed to read carefully. Dropping the object still has an initial velocity of what? 10 meters per second. And where? Upwards. So when it now leaves the hot air balloon, that's when it becomes a free fall. But it will continue for that velocity first, hit the maximum height, and then turn around. In this case, let me clean my 10. Already I see something here, that the velocity here is 5,88. Do you know where I saw my 5,88? There we go. It says this is the velocity time graph of the object, right? But remember, the object was in the hot air balloon. So they both have the same what? Velocity. Make sense? All right. So you see there, so here, that's how it goes. Make sense? This is A, and that is A. Maximum height B, maximum height B. Check. This was what I was trying to explain earlier on. Look at this velocity. 19,6. Look at where we started from. 5,8. The 5,8 was here. But the 19,6 tells me it goes further downwards. Is that making sense? All right. So, point A, point B. This is my point C where it hits the ground. Do you notice our velocity here is negative? And this is point D. What's the velocity? Positive. It means we have changed direction. Do you see the vertical line there? Straight line. It means it's at the same what? Time. So, the object did not stay on the ground. It was instant. CD. All right, just 1 second. And this is what? E. Maximum what? Height. Do you notice it changed direction again? And comes back. Check this. The velocity here is 2,94 and it's negative 2,94 on the same level. If you can just get that interpretation, John. Yes, Leslie. AC. What do you mean by negative? C is negative. No, that's a negative velocity. All right. So what is the velocity here? 5,88. What's the velocity here? 0. What is the velocity at point C? No. C. Negative 19,60. Already you can see that downward was taken as what? Negative. Upward is taken as positive. That is C. Now what is our D? 2,94. What is our E? 0. What is our F? Negative 2,94. I want to show you something here. Look at my graph. Do you see that this here is not at the same height as that? Do you know why? From 19, the object hits the ground with 19,6. It bounces off at what? 2,94. We have lost energy. Energy has been converted into sound, into vibration. It is an inelastic what? Collision. If it was elastic, it will go back to its original what? Height. Because you are saying the velocities are the same. So it has the same power. It has the same energy. But right now, the energies are, the velocities are different. Which means the energies are also what? Different. That's why the object will not bounce back up. If you take a soccer ball and just drop it, it will bounce, but it will not reach the same height anymore. Why? You would hear sound. Where is that sound coming from? It's sound energy. The kinetic energy has been converted into sound. You actually might feel a vibration. So a lot of energy conversions are taking place. That's why the object will keep bouncing until it bounces no more. Because at every bounce, it loses what? Energy. According to the law of conservation of energy. Energy cannot be created or destroyed, but transformed from one form to another. Guys, if you understand the way I did this, you are perfectly done with this whole question. There's nothing that they're going to ask you again. Write down the magnitude of the, please, magnitude. Okay? It's just a number. Of the velocity of the hot air balloon. What is it? 5,88. It doesn't mean you should not write unit. Calculate the height above the ground from which the ball was dropped. Wait. Hold on. Where's the ground? Where's the ground? I want us to use what we've sketched. Where's the ground? Here. Is that fine? So if I'm looking for the height at which the ball was dropped, what letters am I using? This is where it was dropped. This is the ground. C. So we are dealing with between A and C. Can we walk through? Lovely. What do we know? Please write what we know. Velocity at A, everybody, let's write. Let's make it fast. Initial velocity at A. We're writing. 15 minutes, we need to get done. What is velocity at A? 5,88. What's the velocity at C? Negative 19,6. What is our acceleration though? It's negative 9, please use your knowledge of maths now. The gradient is like this. So please, negative 9,8 meters per second squared. Now, between A and C, what time are we using? 2,6. Please, let's calculate, everybody. Use your formula now. Please give me answers. No, it won't work. B is the maximum height. We are looking for where it was. Read the question. Height above the ground from which the ball was dropped. Where was it dropped? At A. Where is the ground? At C. So I don't know if you see that letters will help you. A to C. Please quickly, I want to do a different method, but I want you to calculate first. Anybody, if you have an answer, please throw it in. Let's share answers. Sharing is caring. I need answers, please. We are working between A and what? A and C. All right. Can somebody please type this? Can somebody please give me an answer to this? Can somebody please, Leslie, give me an answer to this? Londa, give me an answer to this. No. Did you do this? Okay, please give me an answer here. Let's walk through. And that first one, I'll write what we're supposed to do. VI is 5,88. Negative? 17,84. So what's our height? Was that what you got? Using equations of motion. All right. 1 second. I'll respond to you just now. Negative 19,6. What's our G? Negative 9,8. And we're looking for delta Y. Is there a formula here? VF squared equals to what? VI squared plus 2A delta Y. Negative 19,6 squared, 5,88 squared plus 2 negative 9,8 delta Y. It gave you the same answer? Yes. As negative 17,84. But we are looking for the height. Height is never negative. You can't say you are negative 3 meters tall. All right, are we okay with this? Do you notice what I did here on the left? Yes, I had questions. I am using what I taught you on graphs. The area under a VT graph is displacement. The area, I've taught you this on graphs. Check your note. Area of velocity time graph is displacement. So, I am looking at point A to C, right? I am always going to use my x as my base. That's a triangle, and that's another triangle there. The x-axis will always be the base. Since it's a triangle, half base times height. Half, what's my first base? 0,6. What is my height? 5,88. All right, remember A, B, and C. But I'm using A to C, right? So I come to the C part. What is my base here? 2. Because it's 0,6 here, and it's 2,6 there. So my base and my height is negative 19,6. Done. Yes, Desmia?
Why don't you use that height as the angle AC and that 19?
The x-axis is where the time is. That's where your base is. This is not your triangle. You cannot use this triangle. That's the rule of physics. We cannot use this triangle. No. Where's our time? Our time is here. So that's what we always do. X-axis will always be the base. So that's my base. So that is triangle 1. And that is what? Triangle 2.
So if the object is in contact with the ground pole, but the second triangle wouldn't be a right angle triangle, so how would you use this method for that?
If the object.
Is in contact with the ground pole a few seconds, right? So you're not going to have a straight line from going back.
No. You still can use because it's just the time frame that is different. You still can calculate that. It's just that line is just telling you the time there and the time here are different. Idris is saying, sir, what's the area under a displacement time? I taught you how to calculate all of these areas. Crash course, 1 minute again. 3 things when you do under graph. 3 things. Number 1, multiply. Do you remember that? Y times X. If that exists, that's what? Area. Number 2, what do? Divide. Y over X. If that formula exists, what do you find? Gradient. And number 3, rearrange. I don't want you to cram it, Idris. Don't cram it. If you have a position time graph, so your position time graph, quickly, this is delta Y and this is what? Delta T. If we multiply, what are we going to get? If we multiply delta Y times what? Delta T. Does this formula exist? Let's ask ourselves. What is velocity? Velocity is what? The change in displacement over change in time. Can we cross multiply? V delta T. Here says delta Y delta T. So it's not going to work. Because that formula will not what? Exist. But if I were to find my gradient, what is my gradient? Delta Y over what? Delta T. Does this formula exist? Yes. That's it there. Which is what? Velocity. So even if I have a graph that is curved, this is grade 10 now. We can create a tangent there and find what we call instantaneous velocity. Velocity at one point. Finding the gradient at a point. Please, guys, go and look for your notes. Go and look for your note. I did explain all of the graph there because examiners not to use equations of motion. So please go and check your note. It's somewhere there in your note. Okay, find those words and I'll interpret. Negative 19,60. Yes. Because we are dealing with displacement. Displacement is a vector quantity. So the negative comes into play. Okay, people, let's quickly answer the rest of. We're just remaining with this small part. 3 questions. All right, guys, quickly, let's answer the next one. Calculate the time. We have 7 minutes. Let's see, can we get this done? Time at the point P indicated on the graph. Where's our point P? There. No, it's the point. That's point where it reaches the maximum height again. It's not the final. But look, it's very simple. How many marks is this? 3 marks or 2 marks. However, this is one thing I know. This is 2,6, right? And this is 3,2. This is the midpoint. Because we spoke about a parabola. All right? So what will be the midpoint? How would you get midpoint in math? X1 plus X2 divided by 2. Please do that for me. 2,6 plus 3,2.
2,9.
2,9. Thank you very much. And we are done with that. So, time at P would be equal to what? Is it 2,6? Plus 3,2 divided by what? 2. What's your answer? 2,9 seconds. We're done. Calculate the maximum height the ball reaches after the first bounce. After the first bounce. Let's check. Let me go to my diagram. Where is the maximum height after the first bounce? What letter represents that? Where is the bounce? The bounce is at C and D. What's the maximum height there? Which letter? E. It's E, not D. We are looking for the height at E. There's a maximum height after the bounce. That's where the bounce occurred. That is. So, do you understand when I say letters and quickly sketching a potential time graph, position time graph? Yes. The velocity time graph will confuse you. So please learn how to transcribe from the VT graph to the position time graph. And everything you need is just right here. All right, let's check. We are looking for the maximum height. What do we know? Guys, do you see we know the velocity here? So let's work with time frames. Do we know the velocity here? Please, let's write it down. Initial velocity is 2,94. We are looking for the height at point E. What do you know about point E? Final velocity is what? 0. What else do we know? Do we need time though? We don't. Because there's Vf squared equals to Vi squared plus 2A delta Y. We're done. What's your A? Negative 9,8. Come, let's calculate. I'm not doing that for you. We're looking for delta Y. Quickly, guys. You also got, okay. Why negative? Do you want to check this for me? What's your answer here? I'm looking for height. I'm using the same method now. You have used equations of motion. I'm trying to work without using equations of what? Motion. The area under a VT graph is displacement. So once they say height, that's displacement. So I am working between D and what? E. That's what we're working with, right? All I needed to do was to calculate what? The area there. Half base time. Do you remember the time here? 2,9. So what's the time here? 0.3. And what's my height? 2.94. Give me 0.44 meters. So the secret is always write down what you have and have a time frame. Work between a particular time. Write the initial, write the final, write whatever you know in between that time frame. You'll be good. Let's look at the last question quickly. It's 2 minutes. What is the last question? Thanks for sending this question. The distance between the ball and the hot air balloon. When the ball is at its maximum height, please read and understand. The distance between what? The ball and the hot air balloon, right? When talks about what? Time. When the ball is at maximum height after the first what? Bounce. Let's quickly get this done. It's so easy. No, our graph is like that, right? So they said when it is at the what? Is that fine with us? After how many seconds was that? 2.9. Remember, the ball was released from here, right? But what was happening to our hot air balloon? It kept moving. Remember, it was rising constantly, right? It kept rising. Is that okay? So when the ball, it took 2.9 seconds for the ball to reach that maximum height. It means the hot air balloon has also traveled for 2.9 seconds. Because we started counting when the ball was dropped. We waited for 2.9 seconds before the ball reached what? Maximum height. It means this guy was also what? Traveling. Still going up in that same what? Time frame. Are we okay? So now, where is this guy after 2.9 seconds? Somewhere up there. But hold on. Do we know the velocity? It's 5.88. Mind you, it is the same. It's constant velocity. Acceleration is equal to what? 0. We're looking for delta y. Do we know time? 2.9 seconds. Let's quickly walk through. Can we get delta y from here? What formula can we use? Delta y is VI. We could have just worked, but let me just work with this. The whole of this is 0. Why? Constant velocity. Acceleration is equal to 0. Do I know my delta y now? Let's calculate. What's my VI? 5.88 times 2.9. What is your answer? Now, we want to finish now. We're looking for the distance. This is where the examiner wants to catch you. You cannot just subtract it. I'm going to try to create something here. Let's see. I hope I'm going to be able to make this easy for everyone. This was where the ball was dropped, right? So this was where we started counting from. Because in this time frame is the 2.9 what? Seconds. How far did we say the object has gone? 17.0. It means from here to here it is what? 17.05 meters. This is where the hot air balloon is now, right? The new place. All right. How far is the object from the ground? We calculated, we got 0.44. All right. So the object is right here. 0.44 meters. What are we looking for? We are looking for the distance. Please, let's be careful. We are looking for the distance from here to here. The distance between them. Don't just subtract. That's the key. They want to just subtract. Are you aware that we don't even know the distance from here to here? So you cannot just say, somebody's already thinking, 17.05 minus 0.44. No. That's why sketching helps a lot. Okay? Already you're saying, but now, do you notice we don't know this middle part? Did we calculate any other height from the beginning? No, I think we did. Didn't we calculate? We calculated the height from which the object was thrown. Calculate the height above the ground from which the ball was dropped. What was that answer? 17,84. Beautiful. Can we go to that illustration? Yes. From here to here is what? 17,84. Are you with me? All right. If I want to subtract, I must use the same frame of reference. How high is the hot air balloon from the ground now? I'm saying from the ground. Because I want to calculate from both of them from the ground. Same frame of reference. 17,84 plus 17,05. What would that give us? 34, do you notice I am measuring from the same point, which is what? The ground. How high is this guy from the ground? 0,44. Now I can subtract. Because I am measuring from the same. So the distance is now what? 34,89 minus 0,44. What's your answer? 34, what? 45 meters. Guys, don't just subtract if they are not from the same point of reference. So we needed to get that height first. I'm done. I hope it makes sense. Yes, your question? G? When you add what? You cannot add because if you add that, there's this space missing. How do you take care of that space? So you cannot calculate the height if we are not standing on the same point of reference. I hope it makes sense. All right, we're good, guys? We're okay? So we see we're seeing tomorrow. We see tomorrow, okay? Tomorrow now we're dealing with electrostatic, the other part, electrostatics, what not for electric effect. Biggie, we'll deal with your question in that stream tomorrow. All right, good night, everybody. The link will be uploaded. You can rewatch the session again. It was quite a beautiful session. Good night, everybody.